by Paul Ho. He's one of the PI for this recent observation of the image of the black hole. So it's really real now, like the previous speaker spoke about. So last year he was also here for the annual meeting, but that was before the announcement of the results. So at this time we have already the announcement. So we are going to hear, I suppose, more about this observation and the insider information. That's yeah, this is the last talk also.
So last year when I came, I couldn't show this because the collaboration says we will really beat on you if you review these results ahead of time, right? So this time I come with the image, which was shown on April 10th. We published 6 papers, and there were 6 simultaneous news conferences across the world, one of which was here in Taipei. And it was on all the newspapers, of course in our local papers, but also internationally on all the main newspapers. And since that time, in this period, in the last year, we've won a number of awards, including the Breakthrough Prize in Fundamental Physics, NSF Diamond Award, CTCI Award in Taipei, and some other awards that are coming that I cannot tell you about yet. But I can say that NSF didn't give us any money, you know, the usual. Thank you very much. But this prize gave us $3 million, which were divided among the about 350 people on the project. So when that happened, a lot of people said, "Why didn't I get on that paper?" You know. But actually, none of these things was as important as getting on the Google banner, right? When you get on the Google banner, you really have an important result. And this, as I understood, the cartoonist made this banner on his way into work in the car, and when he got to the office, he turned into this little cartoon, which captures everything that we want to know. Namely, it sucks everything into the black hole, right? So why is this result important? Particularly for you guys, it's because it's not theory. We're not imagining anything or calculating anything. We're measuring things, okay? And the stuff which used to be thought to be invisible or not able to see it, which is the situation when I got my PhD degree, people asked me, is it possible to do this kind of work in black hole? I said, no, not possible. Well, that's just to show you, in time, everything is possible, right? And this is very important because the black hole, of course, is where we think the gravity will be strongest, and there's no escape. Light cannot come out, information cannot come out except via Hawking radiation over extremely long lifetimes. Small black holes, of course, are important parts of the stellar evolution. That's the end state when the star is 5 to 10 times that of the sun. The leftover after the supernova explosion is the black hole. We know about those. In fact, we see those. Very good evidence of these small black holes. But big black holes, billions times the sun's mass, typically located in the center of the nucleus, is quite strange because we don't know how actually to build those. Whether they're primordial to begin with or whether they have been slowly grown over time, these are all open questions. And of course, black hole physics, this is important for testing general relativity. And I want to emphasize that this particular experiment that we want to tell you about is really about an optics problem. An information retrieval problem for getting to the information that we need. The amount of physics we need are not that difficult. The simple ones, of course, are interesting things such as the energy is proportional to the temperature, of course, so therefore the wavelength that we observe is a reflection of the temperature. And of course, speed of light is limited. This is a very important result from special relativity. Size, of course, depends on distance. More distance the object, it becomes smaller. This is a problem for us because these supermassive black holes are quite far distant. And then, of course, the Doppler motions is quite important. This allows us to distinguish the motions. And this is one of the important results that we derive from this image. And of course, there's energy conservation, is a very important problem. Conservation of angular momentum, very problem. And special relativity and general relativity are also very important parts of this problem, right? So, very important to mention why we do this experiment at the wavelength that we do. Okay, so this experiment is done at submillimeter, which typically has a very characteristic low temperature of about 10 degrees. But most importantly, it sits in the hole in the radiation field because on the surface of the Earth, we are first bothered by extinction of the atmosphere. So basically, we cannot go much shorter than where we were working at, which is about a millimeter, because the atmosphere basically would put too much extinction above us so that we cannot see what we need to see. And what about longer wavelength? Well, actually, longer wavelength is up another problem, which is the scattering effects from the electrons along the way from us to the source. And this has been a well-known problem, which results in a broadening of the image so that we could never quite resolve the image of the black hole previously at the longer wavelength. Okay? So transparency, we need to do the precision, very important precision, in order to do this at this particular energy wavelength. And then, of course, the geometry is very important. You know, the most important part that we want to test here is the general relativistic effects from Einstein, that basically geometry itself is distorted. That's very important because we're not talking about matter, we're talking about light. In that case, bending of the light is no longer done by the dielectric effects, but actually done by the geometry effects due to gravity, right? Gravitational effects on the geometry distorting it forces the light to follow a different pathway, right? Going past a very heavy mass. This ability to bend light or distort the geometry is the key to this particular measurement, namely that around a black hole, there is a shadow region about 5 times the Schwarzschild radius where the light itself is bent because of the geometry distortion, and that bending brings the light into the black hole rather than projected toward us. So looking from here towards the black hole, we will see a shadow which is substantially larger than the Schwarzschild radius by a factor of 5. And that's the important part that we're trying to measure. So no escape from the black hole. This is clear, you know, from special relativity because energy just becomes infinite as the velocity approaches the escape light because the light is limited. That sets a limit, right? So this calculation, of course, allows us to calculate the Schwarzschild radius in the Newtonian way. You get this 2gm over c squared. However, of course, actually this is not right. We have to do it correctly in general relativity, and that calculation turns out to give you the same factor of 2 very nicely. But this is what we're testing. Okay, the metric becomes that the mass over radius becomes a constant. That means when we measure the size scale, physical size scale, we have a direct measure of the mass of the black hole. So that is the metric, right? So again, I want to put the event horizon imaging into the context of black hole research. Last year, I told you about this, so I repeat it again because I imagine nobody remembers from last year's talk. But it's important to say what has happened in this 1 year. Okay, we have some nice results now in the imaging of the event horizon. The other ones are quite slow in bringing new results, okay, but they're very important. There are 3 types of black hole research that we can do, right? We can hear it, we can feel it, and not quite see it, right? Hearing it is, we have about tens of cases, okay? Feeling it, we only have 1. And the orbital motion, we only have 1, okay? In the imaging, we have 2 cases. And all of these things, the most important thing to concentrate on is the fact that they all depend on interferometry as the key on how to do this thing. Interferometry is essentially an optics problem. You have allowing light waves to interfere, and in that interference, there's lots of missing information that we need to retrieve, and we are successful in that. This is then the result, okay? LIGO heard the gravitational waves. These are the standard picture of the LIGO instruments. More are being built all the time. The idea is 2 arms, right? And there's mirrors on either end. You know, a laser bounces in between the interferometry. That is the interferometry, you know, between these 2 mirror. And we measure the slight distortion of these mirrors, right? The slight distortion of mirrors is detected in terms of a strain. Okay, this is the strain ratio, and it's measured at a certain frequency with a certain signal to noise, okay, at the 3 sites. So the signal to noise, you can see the peak is here, and what you see is the strain has this ringing effect, maximum ringing here, and then it dies out, okay? Characteristic time scale, 1/10 of a second of time, right? You know, we see 10 events, we have 10 times 0.1 second of data, okay? And you know, teasing this out is just about impossible, but when you have 3 sites, you can see that it's the same event that's been detected, and it has a frequency profile in terms of the ringing. You can see the compression of this strain that translates to a frequency which is about 50 hertz or 100 hertz, which is why I say it's listening, right? Hearing, that's the frequency that we hear with our ear, and now we have many more cases. The characteristic is always the same, a rising tone in frequency, and then stops very quickly. So in this particular type of research, you know, we are trying to figure out what exactly is the precursor, the root cause of these events, where you have this strong pulse of gravitational wave, which lasts about 1/10 of a second in time, okay? So this now depends on imaging in the optical to look for the precursor. So without that, if you only had, you know, one LIGO, you know, the error circle is actually quite large. This is determined by the fact that you have a couple of arms, you know, in the interferometer, so you can see roughly the delay of the signal, compression signal on these mirrors. That gives you a certain direction in the sky, right? Of course, if you have many of them, then you can triangulate the positioning of the source, but still it's not very good. This particular case, this event is figured to be, you know, in the Magellanica clouds. But the key here is large format optical cameras, okay? I bring this up because Taiwan is involved in this particular project, which is a very large camera on about 1.5 degrees in, well, can I read this? 1.5 degree in the field of view, so that you can image M31 all in one shot, okay? So this particular large camera is made in order to study weak gravitational lensing. This is distortion of the galaxy images in the background, which can be translated to the foreground distortion by weak lensing by a gravitational mask and dark matter in front, okay? So for this particular camera, which is at the prime focus, Taiwan participated in construction of this camera, most importantly on this filter exchanger that we can slip the filters into the lens, in front of the lens of this camera. And this plays a key role because, first of all, that color determines the distance, and that tells us the redshift, so that for this dark matter distribution that we're trying to reconstruct, you can make a 3D map of the dark matter, okay? But the relevance of this particular experiment is that in a very large field of view, a large error circle, we can search it and look for an event, in this case in 2017, an event that faded over time in a number of days, okay? It's that fading of a source in your error circle that suggests that it could be the progenitor. Of course, many things can change in time. Why this particular one, right? So the key there is that you actually can measure the profile of the decay in terms of different wavelengths, and you can fit for that, and it fits the model for a neutron star collision. In that event, we call it a Kilonova event. You can actually model all these decays of the wavelength. And that allows us to determine that this is the most likely model of this particular gravitational event, okay? So the key event here, key important information for this type of study is that, number one, the event is very short. Number two, you can actually identify the progenitors. But the key of both of those statements depends actually on the theory, right? As much as I say this is an observational result, it's the theory predicting this ringing of the collision that's very important for picking out a signature. If you didn't have the theory, a priori, we see this ringing. We don't know what that is, okay? But it's because the theory that has been done over the years tells us that, you know. Now, so this collision theory of neutron star coalescence produce these things, okay? Mind you, of course, none of these models are that sophisticated, right? Do we really understand the physics of merging? That's questionable. Anyway, for this type of field, what are we going to do? There are more number of sources that we can likely detect with the improved statistics. We're hoping that we can see, you know, what type of events dominate such events. Are they neutron star, or black hole collisions? There are different statistics, and the number of events that's detectable will be sorted out when we have enough statistics, okay? But going forward, the in spiral phase, the phase where the source is coming in, slightly beginning this ringing, but actually it's just a rise, very slow rise. And the post-merger phase, which right now, 1/10 of a second, very rapidly decay. These details of this has been suggested to be possible to test first order, second order, third order GR effects that we can wring out through these kind of studies, okay? And in addition, hopefully many more detections, we are worrying about whether we can detect supermassive black hole mergers. So these things are coming. Gravity can also be felt, okay? How do you feel gravity? Well, just like you and I can feel gravity, this is just the attractive force. Of course, the sun pulls the Earth around it, and therefore the black hole also pulls the star around it, and happily in the center of our own galaxy, Milky Way, when you map the star field, you find that the star fields are moving around amazingly, and one of which is moving very accurately on a 15-year orbit, elliptical orbit around the center at one of the foci of that ellipse. So therefore you can calculate what is the mass that's binding this particular elliptical orbit. And that's done very accurately now. And again, we use interferometer. This is in the VLT, the very large telescope interferometer, which is an ESO facility in Chile, 4 8-meter class telescopes together acting as an interferometer. There are also smaller elements which can be added in, but the important point is these 4 elements added together as an interferometer. And it's a very delicate experiment because in the field of view, we actually have to first take a guide star inside this field of view. The guide star is for the purpose of adaptive optics to correct for atmospheric seeing. And then we have a fringe tracking star, and the purpose of that is to track the interferometer baselines very accurately and correct for that. Okay? So this interferometer provides a very high resolution, which I draw your attention to, that with these 6 baselines, it produces a resolution of 3 milliarc second, relative resolution of 40 microarc seconds. Okay? Resolution 3 milliarc second. Figure of merit of an optical telescope is like 1/10 of an arc second. So this is already 100 times better. Okay? And then of course very accurately you can measure relative position by phase because we have an interferometer. And that allows us to get the relative resolution down to 40 microarc second. So what do you see with this? Physicists, we all love drawing diagrams like this, which gives you the confidence that, oh, we can just build this on top of the desk, right? This is just like a benchtop optics experiment. Mirrors, little mirrors. The complicated things, of course, is that you have to have this tremendous delay line because the 2 telescopes are actually slewing the sky. The delay between the 2 telescopes has to be compensated. In the bow of this interferometer, you'll see huge number of mirrors bouncing back and forth, to slow the light down in phase from one telescope to the next. And then after it's corrected, it's poured into these optics, and eventually gets to the detector. You might say, what is the throughput? The throughput is about a few percent of the light actually finally gets to the final detector. So this experiment measured very accurately the orbit. We can actually see the radial motion as well, so that we can fit the line profile in terms of a gravitational motion. We can see these orbits very, very accurately. Okay? But I just draw your attention to one piece of this particular experiment, which is that because they can see the location of the sources very, very accurately to 40 microarc second, they can actually see the movement of a bright spot in the center. And that bright spot seems to rotate in a certain pattern on a certain size scale. Size scale on the order of 100 microarc seconds. Okay? They don't have the ability to image that because the resolution is milliarc seconds, but the relative motion can be accurately measured, and that's why these points can be put together, and they have an orbital velocity of 3/10 of speed of light, likely to be at the so-called the innermost stable circular orbit around the black hole. Okay? Future of this depends on next generation of large telescope. I put that up because in Taiwan, that's what we're trying to do, is to access these very large telescopes. These will, of course, produce more accurate measurements, but more importantly, fainter targets around the center may be detectable, and tracking those orbits may allow us to do very interesting things. Okay. Now, finally, I get on to seeing gravity. Okay, how do you see it? Well, actually, it's not see it, right? Which is not see the black hole, but the black hole itself is very small in terms of apparent size, right? Because even for a black hole of the size of M87, which is billions of solar mass. Its size is only 100 AU, 130 AU, and at 53 million light years, we can calculate the Schwarzschild radius will be 10 micro-arc seconds. Okay. On that order is the Schwarzschild radius, 10 micro-arc seconds. So you can imagine the previous experiment was only at milli-arc second. It does not have the resolution to resolve micro-arc seconds, right? Relative position can get to 40 micro-arc seconds, but you need to get even much better than that optical experiment, right? So compared to the size of the sun and the moon, you know, this black hole is 10 to the minus 9 size of the moon. So it has to be a very precise experiment, okay? So our target is the supermassive black hole. There are two cases, galactic center, M87. They happen to have the right mass, right distance. The shadow is predicted to be about 40 micro-arc seconds. Technique, very long baseline interferometer, sub-millimeter wavelength, precision 10 to the minus 10. Okay, so this you know, M87 is so far away, it is so big, it's about 2,000 times bigger, it's also 2,000 times more distance, so it turns out it's the same angular in size, okay? So to do this, we need to build a telescope, figure merit of telescope, angular resolution, scales as wavelength over size of the telescope, meaning how many wavelengths can you jam inside a telescope diameter. You go to the biggest diameter, size of the Earth, you can figure out what the wavelength you need. Okay? To do this experiment, you just calculate what do you need. It turns out to be about 1 millimeter. As I explained, why 1 millimeter? Because it gets you beyond the scattering of the electrons along the way. If it were longer wavelength, this does not work. The image will be blurred, you cannot resolve it. You need to be shorter than this, okay? Why stop at 1 millimeter? Well, actually, it's pretty hard to get to 1 millimeter. That's why, okay? We would like to be shorter. And we will be shorter, but not yet. Okay? So this is a standard diffraction problem, right? Optics diffraction problem. So what is the experiment? In 2017, we did this experiment. There were a total of 8 telescopes involved. What's interesting here is that Taiwan participates on a lot of them, because we are partners on these telescopes. And we also contributed the atomic clock for the South Pole telescope. So we are heavily engaged, okay? Taiwan is also part of the East Asian Observatory, which operates JCMT, one of the telescopes there, in this 2017 experiment. It's very important to mention Taiwan is part of this East Asian Observatory, which established about 5 years ago in order to build a counterpart to ISCO in Asia, right? At the moment, we have 4 members. You notice these are the national observatories in each of those regions. It's very important to say they're the observatories. We don't say regions, we don't say countries, for obvious reasons. And now we are trying to operate the JCMT for the last 5 years. We access other instruments, and then we're building next generation instruments. That's our plan. And we have been expanding the membership. Now we have Vietnam, Thailand, Malaysia, Indonesia as observers. India is about to join also as observer. And they will also become partner in the future. So very long baseline interferometer, it's basically simulating this very large intercontinental size telescope, right? So you can see the difficulty, okay? You link the telescope by synchronizing the wavefront that reach every telescope. We have to be in phase at that moment, right? So that means the distance between the telescopes have to be precisely known, over 10,000 kilometers at 1/20th of wavelength. Precision of 40 micron over 10,000 kilometers, okay? And then, you know, you have to time the arrival of the wavefront. This is done with an atomic clock. And then you compensate for differential atmospheric effects, that's calibration. Compensate for differential electronic effects, namely the receivers are changing. We have to figure that out. And then the individual response of the telescopes are very different because all the telescopes all have different shapes and sizes. And then finally, the most important part is correct for the fact that the telescope is not filling the aperture that we're doing. Of course, this is the result of a Nobel Prize for Ram Hewish in '74. That image reconstruction is well-known technique that we can make use of. So there are 2 sources. First one is the galactic center. This is a radio image of the galactic center along the plane at centimeter wavelength, 90 centimeter, very splashy radiation. So the size scale here, well, you cannot see that. Half a degree, 75 parsecs is this far, okay? But what you see here, all this splashy stuff at 90 centimeters are probably all supernovas. You can see this characteristic of a ring here and other ring bubbles, okay? And in the center, also a splashy one, which is likely to be a supernova remnant. But if you look very closely to this thing, right in the middle, there's a spiral pattern, and then there's a little spot here which shows up unresolved. This is 8 arc second, a tenth of a second, unresolved point spot in this particular field of view, okay? And the idea of VLBI is that, we would like to greatly increase the resolution on this object, and if we can do that, we are hoping to see something like this, right? Which is, what is actually this stuff which is bright is the stuff that's falling in. The center part should be black, where the black hole is. So that's the imaging process. In M87, we have a similar event. In the optical on the Hubble image, you can see this cluster of light from the center of the galaxy, out of which there's a very thin optical jet that you can see. This is 60 arc second and Hubble image. When you go to the radio, load up the inner part, you can see that it has a very splashy radio O nebula coming out. These are the deceleration surface, active surface of this jet plowing into the intergalactic medium, right? The galaxies is very small in the middle, and then when you keep on blowing up at higher and higher frequency, you find that this jet keeps on going further and further down until over here, you can still not resolve it, but we imagine that there's an engine in the middle, and this is sort of the artist's impression that, there's a black hole in the middle driving this jet coming out. Okay, so that was the theory based on the observations. The observations are actually quite careful. In the optical measurement from Hubble, you can measure the stellar motion around the center of the galaxy, the same way we measure the stellar motion around Sagittarius star. We just track the motion. And from that, they have actually measured two possible masses, 3 times 10 to the 9 or 6 times 10 to the 9. What is the difference? One method is based on gas, the other one is based on stars, which is correct. They could not tell, okay? And then the imaging of the jet in the radio also suggests that the size scale has to be down to that size scale, which is on the order of 20, 40 micro-arc seconds. So this is what we're working with. There are other information that are very interesting. For example, if you actually look at the jet itself, and this is the size scale of the radius of the jet versus the distance from the jet, it follows this on the outside, a conical shape for the jet, but as you get closer, it becomes parabolic in shape of the jet. And most importantly is deriving where is the launching spot of the jet based on these type of measurements. And this says that current data prior to this experiment suggests that the jet actually is within the event horizon area of the source where the jet will be launched. So this is a direct test that we're looking for to see the jet, to see how far in it is, okay? So other things we can do, we can actually do polarization measurements. In other words, we can do rotation measure of the material around the source, and from that you can actually calculate the accretion flow because the matter flowing in will affect the polarization properties. And from this they can estimate the mass accretion rate is on the order of 10 to the minus 2, 10 to the minus 3, the Bondi accretion rate, meaning that this is a very slowly accreting or very starved accretion for the black hole. So that's what we know before, and the experiment is to image it, measure the metric directly, measuring the metric, meaning the size scale, test the general relativity in terms of the light bending around the black hole, measure the mass and spin of the black hole, and then potentially see the jet launching from the black hole. So this is the suggested accretion of the material onto the black hole. We need 10 to the 5 times improvement in resolution. This is in the 1990s, the previous century. Okay. So the appearance of the black hole, of course, depends on the geometry. This is a non-rotating black hole. This is a maximally rotating black hole. You can see the distortion on the shadow. That's because, of course, the light is being dragged differently. And then when there's a disk, which is falling onto the material, the orientation of the disk is very important. It will obscure the shadow because the foreground may be bright from the infall. So again, these things are predicted, but we don't know what they look like. And then, of course, you can predict what the image will look like on an interferometer. We go through the interferometer model to calculate what we will see if we have the interferometer that we have. And then, of course, people also do very fancy things, you know, to calculate the jet as well. If the jet is there, what would it look like depending on the resolution and the placement of the telescope? We simulate all that, and that's where it was last year. I stopped at that point, because I couldn't tell you more, right? But in fact, this experiment took place in 2017. It took us 2 years to process the data, okay? But here's the team deployed to various telescopes, including our staff from Taiwan. And the experiment basically works like this, right? As the source passes overhead, various telescopes come into play, and then the interferometer performs, and we measure the interference between two pairs of telescopes. And as time goes on, this source drifts overhead, other telescopes comes into play, and we collect the data, okay? That is the simulation of what aperture synthesis look like, right? As more and more telescopes rotate in, the aperture is measured, meaning that we actually measure the fringe magnitude and phase at this particular projection of this simulated telescope. And as you see, beginning, very few telescopes are into play, but eventually the data adds up. And then the image gets better and better, depending on how many sources there are, how many telescopes are working, right? Until in the end, this was the final image of this ring, okay? So this aperture synthesis is building up this coverage of the aperture, right? The coverage of the telescope, and the visibility can be thought to be, the measured visibility is just the sampling times the actual source plus the error, right? Why does aperture synthesis work? Is because we know the sampling extremely well, right? That allows us to remove this from the visibility, therefore derive the source. Of course, after correcting the error patterns. The error systematic, this is the errors due to the measurement, like the sky, the receiver noise, and so on, right? But the sampling is the key, is the fact that we know the sampling extremely well. So the calibration is very good because of the telescope armor being constructed. Had it not been constructed, we wouldn't do this, because the extremely high sensitivity armor allow us to correct for the individual response at each telescope. Okay, so you can see before and after, basically amplitude is greatly corrected and the error pattern is greatly beaten down. Okay, so that improves the measurement at every telescope, and the final result was this image. That's the collected data, and this is our processed data. Looks like magic, doesn't it? That's why it took us 2 years. Do you believe that? No, you say? That's because you don't have the right eyeballs, right? Anybody who does interferometry will immediately say, oh, that's an interference pattern, right? From lack of information in a certain direction, right? All these error patterns is well understood as the interference pattern. So we do a lot of things like, you know, carefully sorting the UV data, the visibility. We clean, which means that we correct for the error pattern. We self-calibrate. That means that we use the reference information between telescopes. We have redundant information. When you have 3 telescopes, if you measure 2 pairs of response, it constrains the 3rd one, right? So from this, we derive this wonderful image. We have 4 separate teams doing this processing because people were worried. I would say people who worried were the theoreticians because they didn't believe interferometry actually works. For us who do interferometry, we would just immediately go to this and say, just do it. But they had derived all sorts of different methods in order to try to correct for this image. And in the end, they all get something like this. And these are the model of what it could be, right? Is this a ring? Is this a crescent? Is this a disk? Is this a double source? You look at these images, it's clear it's this one, right? It's a crescent. It's definitely not a filled disk, definitely not double, it's definitely not uniform, right? So, how about time variability? Turns out that over 3 days of the experiment, separated by a few days, we have a window of 10 days during which we took data, and you find that the image roughly is the same from every day, every epoch. Okay, roughly the same, except on large scale there's slight differences, meaning that this fluffy stuff changes a little bit. On the small scale it's very stable. This is very good news for us because the small scale correspond to the longest baselines and therefore likely to be effects at the horizon, and they appear to be stable. That means that we have a chance to tease that out in time. Okay, in time, meaning that when we have many more measurements. How about how do we predict versus what do we measure? This is actually the proposal led by our team. This was the proposed prediction of what the image will look like, and this is the end result that we measure. Pretty close, right? But not quite. The image is flipped, and you will say, what's wrong with you guys? Can't you get that right? The answer is, we don't know the spin, okay? So, here's the answer. What do we actually measure? What does the image say? People ask me, I say, well, it looks black, looks like a hole, must be a black hole. And the size scale, this turns out to be the Pluto's orbit around the sun, and this is where Voyager has ended up by now, right? 42 micro-arc seconds is what we measure. Remember, this is only for relative measurement, they were good to 40 micro-arc second for the optical measurement. For radio measurement, we have resolved the image at much better than 40 micro-arc second in order to see the stuff. What does it mean? Photon ring at 42 micro-arc seconds, 400 AU round, implies, if it's 5.2 times the Schwarzschild radius, calculate that, as expected by general relativity, reduced mass, 6.5 billion times solar mass. Remember the measurement from stellar motion, it's either 3 or 6. So 3 is definitely wrong, 6 is right. Okay? So that's a clean measurement, independent. What does it say? It says, what the stellar motion outside sees the binding mass of 6 million solar mass, it's all inside this 42 micro-arc seconds. All the mass is concentrated in that dot, okay? So you can calculate that, of course, you know, this looks like a black hole. This is a massive black hole. But it's not bigger. That's also very important, right? You could have gotten a size that's bigger than this. Then you would imply a mass bigger than 6 million solar mass, 6 billion solar mass. Then the stellar motions outside would be wrong, okay? You will see greater rotation speed. You don't. So this is a very good confirmation that this particular number, 5 times Schwarzschild radius, is correct, where the mass is already pinned down in agreement with other measurements. Okay? The brightness of the ring itself can be measured, and then from that through a little bit of theory, we can actually calculate the mass density of the plasma, magnetic field to be guessed at, and the accretion rate, again, 10 to the minus 3, just very close to the previous measurement from the polarization, saying that this is a star black hole. Okay? Very important, the ring asymmetry, brighter on the bottom side. Okay? That comes back to why was this important for the Doppler motion that I mentioned in the first slides. The Doppler motion allows the part that's pointed towards you to be boosted in energy, right? Because the frequency of the waves are compressed. The part that's away from you is dimmer because the waves are pulled apart. So this is a clean signature of rotation. But it has a very important constraint. If this is rotation, you can't get the brightness to be distributed in some random pattern. It has to be brighter on one side, dimmer on the other, right? Half and half. That's what that is. Brighter on one side, dimmer on the other side, right? So this tells us this part is coming toward us, this part is going away. And furthermore, it has to be a rotating thing, it has to be a disk. Okay, so tip disk, we can then measure the tipping of the disk. Turns out that it is indeed perpendicular to the relativistic jet on the large scale, and the spin of the black hole now, we can tell by right-hand rule, it's away from us. Okay, so that's what we got wrong in the proposal. We didn't know the spin. If you guessed the other way, we would have gotten the orientation of the bright and the light part. Okay, why is this spin part so easily constrained? That's because if you look at the accretion flow on the outside, whether it's rotating this way, clockwise, or counterclockwise, it doesn't matter. When you get close to the black hole, you are constrained by the spin of the black hole. Okay? If the spin is this way, the innermost part has to follow. That's because it's under the drag of the geometry, right? So the outer part doesn't really matter. When you see the inner part, it's defining the spin. So the inner part defines the spin. Away from us, the bottom is brighter. Okay? So that's just the orientation. The inner rotation has to be locked to the black hole rotation. So here's the simulation of the Doppler boosting. On the left side, phase on, this is the accretion, model of the light. On the right side, we're tipping this disk. And as you see, when the disk is tipped, one part is brighter, the other part is fainter. That's just come from the Doppler boosting as we calculated. Okay? So that's the calculation. And then there's the idea of what does it look like compared to the observation. So on the right side is the model, on the left side is the observations. And what you see here on the right side is just convolving the model to the resolution of the experiment. Okay? What you see is that the model, when it's smooth, convolved to the resolution of the experiment, it resembles the observation. That's a good thing. Bad thing, 90% of the models we calculate did the same thing. Meaning, resolution not good enough, right? We cannot distinguish all the various models. Okay, that's still to be done. Okay, so what can I today tell you and not tell you? Told you about the M87, but I cannot tell you about the galactic center, which I've seen, but I cannot tell you. I can tell you the results are very exciting, but I cannot tell you. But I can tell you that the M87 is not wrong after seeing the saturated stuff. Okay, so that means that the image is consistent with that interpretation. But in a few months, I can tell you the next image. M87 also has the GLT data in 2018, which means that image will be coming for that database, which will be sharper because we have the northern part extended. Okay? Polarization data has also been taken, not fully analyzed, but that also will happen. We also have a set of data on AGNs doing these experiments. Those will also be coming. Those are jets, right? So in the experiment in 2020, in a few months, it will be much better because we have new stations coming in. The GLT itself has been upgraded so that the surface is much better. And we have a new receiver at JCMT that's 4 times sensitivity. These are things that we are working on in Taiwan. The Iran NOEMA interferometer will be available as a single dish. I don't know its final sensitivity, but it will be added. There's a couple of more telescopes that might come in. So key here is that Asia will play a leading role in this particular type of study. Okay? Summary, current research all depends on resolution. Obviously, gravitational waves, of course, is handling the coalescence problem. The optical interferometry is handling the dynamics problem around the event horizon. And the submillimeter is actually imaging the black hole itself in the event horizon and looking forward to testing more detailed physics and the GR effects closer to the horizon. The next generation stuff is all going to be much more sensitive. We are hoping for more resolution, of course, but also enough sensitivity that we can begin to look at the time domain, energy domain, and dynamics domain. So I can mention, even though I cannot show you the image, the reason why the galactic center is difficult is because it is actually a much faster rotating object on the sky. Its rotation period is on the order of hours, whereas M87 is on the order of months. So hours means while we're imaging, the image is changing, right? That's why it's difficult to get the results correct at this moment that everybody can be satisfied with. But it can forecast what it means, right? It means that next time around, I won't be showing you an image, I'll be showing you a movie of what happens around the galactic center. Okay? So, again, Asia will play a leading role into the future. I can say, where are the problems? The problems are getting down to the problem that we only have 2 targets at the moment, okay? We're going to have to improve the resolution by a higher order, a factor of 10 or more. This is what we're going to do when we bring the Greenland telescope to the summit of Greenland. We will go 3 times shorter in wavelength, 10 times higher resolution. Milliparsec problem. These are the milliparsec problems. We're hoping to see the merging black hole binaries, right? The question is, what size scale will we do, okay? And then there are potential in this particular method to see binary black holes that so far we have not been able to resolve in external galaxies. And then, of course, we now know that it's rotating, but how much this has to be actually sharpened up so that we can tell you what exactly the spin is, okay? And then there's astrophysics to be done, in terms of accretion and launching of the jet. And these are things to be done when we have more sensitivity, okay? And then, of course, you have to think about how we're going to do this, to probe other things, right? Okay. Stop there.
Thank you very much. Okay.
Do you measure polarization? And if so, can you say something about magnetic field near black hole?
So the magnetic field in the black hole, we don't know yet, right? So only from the plasma, we are measuring the plasma radiation. And from that, from the brightness, we can simulate or we can calculate what we might expect depending on what the magnetic field strength is, right? Because these are synchrotron radiation, so you will see, what the radiation will look like, strength in terms of B. But it's not an independent measurement, right? So we probably need a little bit more assumption and modeling in order to get that right.
No other questions? Okay.
Could we have a chance to see, for example, a merging neutron star? The
So neutron stars are very faint in the radio, right? But when they merge, of course, they give you this burst of gravitational wave. So that's why we can see the neutron star merging as a ringing pattern on the gravitational wave experiment, right? But because we don't see it until it actually rings, we don't have an idea of how to search for them in the in-spiral phase, which is pre-merger, okay? But improved sensitivity means that we will probably be able to see perhaps things that are rising, and therefore may be able to track the early phase before the actual objects are merged. So that's the hope of the next generation gravitational wave experiment, is to be able good enough to catch the ringing phase early enough to follow up immediately. So how early is that, you say? Well, the in-spiral phase is only minutes. So this is a very difficult experiment, right? You have to see it and immediately turn on all the telescopes to look. So that's very difficult.
Apart from the shadow, assuming you have improved the sensitivity and resolution, can you see other structure of the black hole, like a jet or maybe?
Yes. So the jet should be there. We don't see it at the moment, but I think that is because we don't have enough confidence in that image, right? I'm going to go back to the first image. Actually, if you look at it, the light is not good enough for you to see it. Okay? If you turn off all the light, you'll see some faint stuff around. Okay? Most people will argue with each other whether the faint stuff is real or not. Okay? But it can be very well that the jet is like this and like that, and we see the inner parts of the jet very faintly. So we need to boost in sensitivity in order to resolve out these external features that are outside of this ring. Okay. So I'm actually pretty confident we will find the jet with a little bit more sensitivity.
So time scale, you think you may be able to tell us about this?
The jet?
Yeah.
Well, we are taking experiments every year, and we're trying to improve the sensitivity every year. So the upcoming experiment will be improved by a factor of few already. So how do you improve the sensitivity? Usually we broaden the bandwidth that we record. In other words, if you expand the bandwidth of the experiment, you capture more light, then you have more sensitivity. Right? So we're just working on that at the moment to get the receivers to have the right response.
Okay. Any more questions or comments? Okay, no. Let's thank Paul again. All the speakers of the morning and the whole conference. So on behalf of NCTS, I would like to thank all of you for coming to make this a very successful and memorable event. In addition to the organizer, we would also like to thank the secretary, so that Candy and other people outside. So we're thanking them. Okay, can we? Okay. Thank you. And other people, yeah. And the organizer, including myself, but I'm told in particular by Sabong that to remind you that your per diem has include the hotel fees. So you have to, when you check out, you have to pay the hotel. Yeah. And okay, so I would give Sabong, do you have any final remarks?
Well, just remind a few things. Of course, thank you very much for coming and meeting. We made you really work early in the morning, 8:30. But then we save one afternoon. Maybe you can look around a little bit. So after this, you pick up the lunch box outside. But this room will be closed at 2 o'clock. But on the 5th floor, the NCTS, the offices will be able to open and some of them, and then you can relax there or continue to work your next conference talks. Yeah, right. Some of you probably are doing that. So thank you for those of our friends coming from far and those are locals. Without your participation, without